Modern foundational models possess immense reasoning capabilities, but they are entirely isolated from the external environments they attempt to analyze. Historically, engineers bypass this isolation by writing bespoke function calling integrations and manually wiring APIs for every individual data source. This creates what developers call the N times M integration bottleneck. Every time a large language model needs to extract data from a new enterprise tool, developers must write custom glue code. Connecting N models to M database modes creates a combinatorial explosion of intersecting, unmanageable API connections. This manual wiring approach fails to scale. And as endpoints update or models deprecate, the custom code fractures, resulting in a brittle system carrying massive maintenance overhead. Without a standardized transport layer to govern these connections, AI agents remain trapped in isolated silos, effectively crippling enterprise adoption. This document outlines the Model Context Protocol, or MCP, a modular framework designed to solve this exact problem by standardizing AI-driven data integration. Anthropic released MCP in November 2024 as an open source standard, backed immediately by widespread industry adoption. To understand how it works, let's look at the Language Server Protocol, or LSP. Before LSP, every text editor needed a custom plugin for every programming language. LSP created a single universal standard that unified the entire IDE ecosystem. MCP applies this exact architectural logic to artificial intelligence. It decouples the model's underlying intelligence from the raw data access it requires to function. Mathematically, this collapses the integration complexity. Instead of maintaining an N times M web of individual connections, developers build to a single protocol layer, creating a clean N plus M hub and spoke topology. By treating external systems as first-class components through a universal port, MCP allows AI to transition from static text generators into dynamic, interactive agents. The architecture starts with the MCP host, the application containing the large language model. Inside sits the MCP client, translating external communication. Outside, the MCP server connects to local or enterprise databases, exposing capabilities. MCP enforces a strict one-to-one connection between client and server. Because of this constraint, if a large language model needs to query a database, read a local file, and search the web, the host application must instantiate 3 distinct clients to manage that multi-tool ecosystem. This strict topological separation ensures that large language models never directly handle external API authentication. The client abstracts away all the complex routing logic and credential management. Across this network architecture, the protocol relies on continuous stateful data packets flowing back and forth between the client and the server. All protocol interactions are required to use JSON RPC 2.0. This is a stateless, lightweight remote procedure call protocol that uses JSON to format requests and responses. This continuous session management allows the AI to maintain context over time, contrasting sharply with traditional REST API calls that treat every request as an isolated, stateless event. To move data, MCP uses 2 transport mechanisms. First is a STDO, or Standard Input-Output Layer, strictly for local process communication on the host machine. The second uses HTTP combined with Server-Sent Events, or SSE, handling remote communication to receive automatic asynchronous updates. This dual transport layer allows the large language model to orchestrate local file systems and remote cloud databases simultaneously, routing everything through the exact same JSON RPC interface. A server exposes its environment via 3 primitives. Resources provide read-only file access. Tools are active functions with strictly typed schemas, ensuring the large language model understands inputs before execution. And finally, prompts are reusable workflow templates that standardize tasks and instruct the model. The entire lifecycle follows a strict sequence. First, client and server negotiate. Next, the LLM requests a tool. Then the client formats the request. Finally, the server executes the action. By rigidly typing how the AI interacts with its environment, MCP eliminates prompt bloat and removes the guesswork inherent in traditional tool execution. Solving the integration bottleneck through a universal protocol successfully connects AI to the real world, but granting autonomous access introduces severe structural security vulnerabilities. MCP is merely a transport protocol. It lacks native centralized authentication mechanisms, deliberately offloading all security, authorization, and permission controls to the simple implementer. Granting a language model arbitrary data access and active code execution paths massively expands the attack surface of the entire enterprise system. The primary threat vector is prompt injection, where a malicious payload enters the system disguised as passive data. Once ingested, it moves from the resource layer through the client and tricks the large language model into executing an unintended action in the active tools layer. This works because of the LLM's cacophony, the inherent tendency of AI models to blindly comply with instructions. The model cannot differentiate between a passive context document and an active malicious instruction hidden within. Deploying MCP in enterprise environments requires rigorous zero-trust wrappers. Because the protocol natively trusts data it has fed, the surrounding architecture must verify every interaction. Despite the security overhead, MCP achieves a critical architectural milestone. It standardizes the hands of an AI system, granting models a predictable method for real-world interaction. This research analysis examines MCP in high-volume fintech environments, demonstrating how the protocol resolves severe latency issues and interpretability bottlenecks in complex financial workflows. It accelerates the transition from models that merely generate static text to autonomous agents capable of deterministic, multi-step environmental execution. The extreme fragility of bespoke point-to-point integration is replaced by the robust resilience of standardized schemas. As adoption scales across major AI providers, this universal port will serve as the foundational technical substrate for the emerging agentic economy. The Model Context Protocol acts as the architectural bridge that finally allows the isolated foundational models to safely, securely, and predictably execute real-world operations at scale. Copying and pasting patient data into a public web chatbot is a massive security risk. Dragging highly sensitive information over to an external browser hands it directly to a third-party server. HIPAA is a U.S. law that mandates strict privacy standards for protecting medical information, and this kind of exposure violates those legal protections. A better approach is an AI assistant that lives exactly where your data does, on your local machine. Instead of sending data out, the assistant queries your local databases directly. It pulls exactly what it needs when it needs it without you ever touching the clipboard or exposing data to a public web API. So to make this local connection possible, we use the Model Context Protocol, or MCP. MCP is an open standard that allows AI models to securely connect to your local data sources and tools using a unified communication language. To build this architecture, we need three things: Python 3.10 or higher, an AI host application like Claude Desktop or the Cursor IDE, and the UV package manager. UV is a fast Python tool used to manage project dependencies in virtual environments. Configuring these local tools provides the privacy layer necessary to handle medical data, ensuring it remains within your controlled environment throughout the entire processing lifecycle. This flowchart illustrates MCP's three components. First, the host application. Next, the internal client translates requests. Finally, the server securely touches your local database. Building this with the raw SDK requires complex boilerplate, but FastMCP reduces all that plumbing down to simple decorators. Step one is setting up our environment. We're going to open our terminal, use UV to initialize a directory, and install the FastMCP library. By relying on FastMCP to handle the intricate network plumbing, we spend our time writing actual secure business logic instead of wiring up connections. Now, once the environment is ready, we need to give the AI access to our data using a resource. A resource acts like a secure read-only endpoint that provides static context directly to the model. So, in your code editor, start by writing a standard Python function designed to fetch a specific patient's record from the local database. Then, you place the @MCP decorator directly above that function. This tells the server to expose this data. This single decorator safely exposes local database rows to the AI model without opening any public web ports. While resources provide static data, tools provide functionality. A tool is an actionable computation or execution the large language model can perform on demand. To give the LLM capabilities, write a secondary Python function designed to calculate BMI or flag abnormal vitals. Applying the @MCP tool decorator right above this new calculation function grants the AI the permission needed to run it. By defining these tools, the AI gains the ability to perform its own calculations and logical checks on the records it retrieves. Before we run this code, we must avoid the common setup mistake, using standard Python print statements for diagnostic tracking. Standard print text physically corrupts JSON RPC messages over local standard input and output channels, crashing your server. To fix this, always use the built-in Python logging module and explicitly route your diagnostic logs to standard error or stder. Logically, isolating your diagnostic logs from the server's primary data stream is mandatory for this zero exposure architecture to function. With the code written, type FastMCP dev in your terminal to launch the local testing environment. This opens the web-based MCP inspector. Here, developers manually trigger tools and verify the server returns a successful JSON output schema before ever involving the large language model. Once everything checks out, run FastMCP install. This command automatically registers your new healthcare server with your host application's configuration file. Now, transition to the Claude desktop interface, or similar. Input a prompt asking the AI to look up a specific patient ID, read their record, and analyze their vitals. The host application recognizes the available tools and immediately halts. It requests your explicit approval before executing the local get patient record and analyze vitals tools. This multi-step localized execution proves the zero exposure security model operates exactly as intended in a real-world scenario. After approval, the AI orchestrates both the data retrieval and the calculation, outputting a synthesized health report. You have now granted an AI model secure local database access using standard Python, allowing it to work with private information it was never originally trained on. As you move this from a local machine to an enterprise production environment, the next logical hurdle is restricting exactly which users and which AI agents have the authorization to run these local tools. For that, developers use tools like Cerbos. Cerbos is an authorization layer that adds granular permission management and role-based access checks directly into your MCP servers. Replacing unmanaged web prompts with these localized tools creates a system where AI agents can safely authorize within an organization's private infrastructure.